5 minutes more on R. I brought a slide, not so interesting. Let's look instead on what we have done already. The main thing to add, of course, is the following, that we don't have to do sort of hand calculations by R. Everything is built in, of course, in a function. The important function is called LM. LM stands for linear model. So there is a function in R that can take, and the syntax to be used is to write y tilde x. That is a function expression in R, or a model expression in R, actually, generically, where y is a model of x is written by y tilde x. That's the way it's put. And in fact, that's a generic expression that can be used in different functions, but that's a bit R technical. Here it's used for the obvious to make the linear regression, and then I apply directly the summary function to this linear model result, and let's see what kind of story that R is telling me here. This is what I'm requiring of you to be able to get some meaningful out of such an output, if you see it. And I think it's not really that difficult to get some meaning. Given what I've taught you now, it's not that difficult. It tells some stories about the residuals. Residuals, that are the deviations from the line. So it sort of tells a bit of indications of that the smallest residual, the smallest guy on weight is 18 kilos below what is expected by the line. The most weird heavy guy is 11 kilo, guy or girl here, 11 kilo above what the line is expecting, and so forth. And here is the important thing, given the intercept and slope thing that I told you. It uses the term intercept. It uses the name height because x, the x input is height here. And it tells me what I already computed. It tells me the A and the B, right? On the coefficient, under the heading coefficients. It also gives me the standard error. The standard error is the thing I wrote out on my slide before, the sampling distribution standard deviation of the thing. This is a thing, it could be the slope, it could be the intercept. This is the one used in, this is the number used in the confidence intervals formulas, the number here. Of course, you can read what I'm saying here, you can read in my R note, that's why. This is what I require of you at the exam, that you should be able to know this. Or at least find it when you're there, because you can bring the note, so you don't have to remember everything, but you should know that it's there. Otherwise, it would take too long time to find it if you don't even know it's there. You get the t-values for the hypothesis tests, and you get the p-values. And let us forget about the intercept, because it's not very interesting that the intercept is not 0. Because that was good, I got that out of my mouth, because what R by default is doing is making a hypothesis test for the thing being 0. For the intercept, usually it doesn't make sense. For the slope, usually it's the core test we want to make often. Is there a relationship? The p-value is 0.000007. So looking at this picture, yes, I'm goddamn sure there is a relationship between weight and height. Right? What is the relationship? The relationship is 1.2 kilos with a standard error of 0.2. So a confidence interval would be something like 1.2 plus minus twice this number. Twice meaning a t percentile, really. Okay. You also get the SE number. The SE number is here, the 8, as I computed myself from before. And that's basically, you also get the squared correlation. You get the squared correlation, not the correlation. The correlation was 0.77 something, we computed that before. 61% of your height variability is, I try again. 61% of your weight differences, weight variability, is explained by your height. The remaining 39% is biological variability for people of your type, right? That's the interpretation. One more thing before we leave each other today. We can also go check whether it looks like the linear. In the beginning I said look at the data, so definitely always make the plot. Is there really a linear relationship? We have to be somewhat worried about that. There are diagnostic sort of recommendations to what can you do to investigate this generally. What you can do is to actually take the residuals out of, I can rapidly in R compute all the residuals, that is all the deviations from the lines. And here I have all the deviations. And then I could, for instance, I could do a histogram of these deviations and see if it follows a normal distribution, for example. That's part of the model. I could also do a normal plot of the, as I taught you previously, to check whether the deviations from the line, this is checking whether some of my assumptions here are okay for doing all the statistics. And if we had more time in our course, of course, we would spend an hour on discussing in detail how to do such diagnostics for linear modeling. That's very important. But to get more of those details, you should come back and get more nice courses in our stats department to be more experts in doing that. At the final lecture, I've given you some commercials of some of the nice courses you can take for becoming better at this. There are other ways of looking at whether there is systematic changes, if there is a parabolic on all. This is looking at residuals. That's fun, but not today because we're finished. Enjoy the work out there. We have one more topic day and then a summary day in this course. So I hope to see you again and enjoy the day.